And welcome back. Okay, so in this video, we're going to look at how to write the electronic configuration of elements. So hopefully, by the end of this video, you'll be able to write the electronic configuration of the first 30 elements up until zinc. And you should be able to represent the electronic configurations using orbital diagrams and know how to fill these up properly. So first of all, I'm just going to bring you back to a couple of slides you've already seen in one of the previous videos. Now, we went through the basics of how electrons are organized within an atom. We discussed quantum shells, which you just know as shells. We then looked at subshells. Okay. We then looked at the orbital diagrams. Okay. Now, we're going to be using those today. We're also going to be looking at the fourth quantum number, which is spin of electrons. Now, we also looked at this slide here. Okay, so just as a reminder, so for the first three shells, first shell contains an S subshell, second shell contains an S and a P, third shell contains an S, a P, and a D. Now, each of these subshells can contain different numbers of electrons. So an S can contain 2 electrons, a P can contain 6, and a D can contain 10, meaning our 3 shells have a different maximum number of electrons they can contain. Okay, now the first thing I'm just going to do is to introduce you to orbital diagrams. Now, they're very, very simple. For instance, an S subshell contains only one orbital. Now, an orbital is just represented as a square. Now, the P subshell contains 3 orbitals. So we represent this as 3 squares put together. This is representing Px, Py, and Pz. And finally, D. Now, a D subshell contains 5 different orbitals. So I'm going to represent that with 5 squares together. Okay. Now, hopefully you can remember the names of these different orbitals. Now, the order of these names corresponding to the boxes doesn't really matter, especially in terms of your A level. Okay, but you do need to be aware that a D subshell has 5 different orbitals. Okay, so the next bit of information, how would you show electrons in these orbitals? Well, you do that with arrows. Now, each box can contain 2 electrons, because each orbital can contain 2 electrons. Now, the first electron in an orbital you represent with an up arrow. This is representing what we call up spin. Now, electrons cannot be in the same orbital with the same spin. You don't really have to understand what this means, okay? But you do have to know how to apply it to orbital diagrams. So if you are adding a second electron, you do it with a down arrow. Okay? These 2 electrons have different spins. Therefore, they can be in the same orbital. Now, that's nice and easy for S, because there's only one orbital. But when you're working on P or D, you have to be aware of how to order the electrons. Now, the first electron into a P subshell will go into the Px orbital. Now, you might be thinking that the next electron would just also go there because it can contain 2. But I'm afraid it doesn't. Now, when electrons are in the same orbital, they repel each other. Now, as much as possible, your atoms want to minimize repulsion because that puts the atom at a higher energy level. So, for the second electron in a P subshell, it would go into the Py orbital. And the third one would go into the Pz. Now, at this point, each of the orbitals contains 1 electron. Therefore, the next electron has to pair up. So at the moment, these three are unpaired electrons, but the next electron has to pair up with an electron in one of the orbitals. And then you can keep on adding like this. Now these same principles apply for the D subshell. Draw your up arrows first, but you have to put one electron in each of the orbitals before you pair them up. So once each orbital contains one electron, the next electron will go into an orbital which already contains one electron. And then you can just carry on. Okay, so that's the basics of orbital diagrams. Each box represents one orbital. Each orbital can contain 2 electrons. Within a subshell, each orbital has to contain 1 electron before you pair them up. That's all you really need to know. Okay, so let's apply this to actual examples. Now, first of all, I'm just going to draw in the orbital diagrams. Okay, you might think I've made a mistake with how I've drawn these, but you'll see this is how it's supposed to be in a little bit. Okay, so we're going to go through all the elements. I'm going to write the electronic configuration on the right hand side, and I'm going to draw in to the orbital diagrams on the left. So let's start with hydrogen. Okay, so hydrogen only contains the 1 electron. Now you always start towards the center of the atom at the lowest energy level, which is the 1s. So first electron goes into the 1s subshell. So the way we write this, a large one, which represents first shell, S, which represents the subshell, and a small one. This represents the number of electrons in that subshell. Now for hydrogen, there's only 1, so this is the most simple example. Now helium comes next. Now previously we said that each orbital needs to contain 1 electron before you pair it up. That was just for a specific subshell. You must fill up one subshell before you move on to the next. So this second electron also goes into the 1s subshell. Remember to put your arrow pointing the other direction, representing the opposite spin. So for helium, first quantum shell, S subshell, 2 electrons present. Okay, so now lithium. Now the 1s subshell is already full. It can only contain the 2 electrons. So the next electron must go into the next subshell. Now the 2s is higher up in energy than the 1s. Therefore, you can only put electrons into the 2s if you've already filled the 1s, which we already have. So this third electron goes into the 2s. So for lithium, you start at the beginning, so the 1s, 2, but then we also have 2s1. This tells us that there are 2 electrons in the s subshell of the first quantum shell, and 1 electron in the s subshell of the second quantum shell. Beryllium, we just fill up this 2s subshell. So again, start at the beginning, 1s2, we now have 2s2 as well. That's the 4 electrons in total which are present in beryllium. Now with boron, we are now moving in to our first p subshell. So the electron goes into the px orbital. So we now have 1 electron in the p subshell. So we end our electronic configuration at 2p1. Now don't forget, next we need to fill up each orbital within a subshell before we pair up the electrons. So next electron goes here, and for nitrogen it goes into that third orbital. Now once you're at this stage, the next electron has to pair up. So for oxygen, the electron goes in here, but the electronic configuration just follows on with the same pattern. Then we have fluorine, and then neon, which fills up the 2p subshell. Okay, so hopefully you're starting to notice a pattern which we looked at in one of the previous videos. We went through that you had an S block and a P block, and that is to do with the outermost electron, into which subshell it belongs. Now for 3s and 3p, it just follows the same pattern. So I'll quickly write them down, but I won't do any explaining because it just follows the same pattern as we've just done. So I'm going to rub out these examples so that I have some space. Then I'm going to continue with the 3s and 3p. Okay, so they just followed the same pattern that you'd seen previously. Now we're up to argon. So from now on, I'm going to start my electronic configuration by doing this. Now this just represents the electronic configuration of argon. You may see this in your exam questions. It is an acceptable way of writing the elements with more electrons in them. Now at this point, you'll notice that we're not going to go into the 3D. Now if you follow on the periodic table, the next element is potassium. Now you can see potassium is in the S block. The 4s subshell is actually slightly lower in energy than the 3D. So we fill up the 4s subshell first. So for potassium, start with the electronic configuration of argon, then it is 4s1. Calcium is also in the S block, and now that that is full, we now go into the 3D. Now it's acceptable to write the 4s first, like I've done, or you can have the 3D first and then the 4s. Either is acceptable. Now 3D behaves just like the p subshells. You need to fill each orbital with one electron before you pair them up. Okay, so we're now up to chromium. Now, chromium is one of two anomalies in this process. So I want to bring your attention to this. Now from our pattern so far, you would predict that you just put in one more electron into the 3D subshell, and that is correct. But there's also a catch. Now with the 3D subshell, it is very close in energy to the 4s, much closer than between any of the other subshells. So that means it does not take too much energy to promote one of the 4s electrons into the 3D subshell. Now in this case, having one electron in each orbital would provide a balance which actually lowers the energy of the atom. So what actually happens is one of the 4s electrons is promoted to the 5th 3D orbital. So for chromium, we actually get 4s1 3d5. Now this is an anomaly, doesn't follow the same pattern, but it is one they like to ask you about in your exams. So make sure you remember this. Now with the next one, with manganese, you just fill up the 4s subshell again so that it appears to still be following the same pattern. And then you just carry on as normal until we get to this stage. Now we have the second anomaly, and it follows the same sort of reasoning as our first. So with copper, we add in our extra electron, but now this 3D subshell is completely full apart from one electron. Now again, it would be lower in energy if it had a balanced 3D subshell. And because 3D and 4s are quite similar in energy, you're able to promote one electron. So for copper, you get 4s1, So I'm just highlighting the two anomalies here. Where an electron has been promoted from the 4s subshell to the 3d to provide balance, which allows your element to be at a lower energy level than it would be otherwise. So you can see here both these elements begin with C. I know we have cobalt as well, but if you see a D block element beginning with C, alarm bells should be going off in your mind. Okay, it's a trick. Do not forget the anomalies. Okay, and we'll just finish off with zinc. Zinc just fills up for a subshell. And there we go. All 30 elements that you need to know. You need to be able to write the electronic configuration, which I did on the right hand side. You might also need to draw the orbital diagrams, which I did on the left. So make sure you can fill them up properly. Don't forget to start at the lowest energy subshell possible, and that one needs to be filled before moving on to the next one. Do not forget that an orbital does not pair up electrons unless it has to. For a P or a D subshell, you put one electron in each orbital before pairing them up. And don't forget the two anomalies, chromium and copper. Okay, that was quite a long video, but these are the fundamentals. Content in this video always comes up in exams, so make sure you know how to do this. So hopefully you can now write the electronic configurations for the first 30 elements and be able to correctly fill in the orbital diagrams. Make sure you've completed your notes, and if you have any questions, please ask me in class.